Alrighty, statisticians, last video for 3.3. Let's put together everything we've talked about so far. So what we've talked about so far is we've talked about power models. What happens when I raise x to a power? We've taken the logarithm of both sides of my equations, and we've looked at what happens. We've also made x the exponent, which is the same as taking the natural log or the log of both sides. And we've looked at our residual plots to determine which model would be the most appropriate model to use to predict outcomes instead of just the original data. So what we are going to do today is we're going to figure out which of these models is the best to predict data within my x values. So what we are going to do, I got a little itch. We're going to choose the model with the residual plot that has the most random scatter plot. Remember, we don't like our residual plots to have curves. And if there's more than one model that you think is as random as any other one, look at your coefficient of determination, your R squared. Which one is closest to 1? The one closest to 1 will be the correct one to use if you can't tell by the residual plots. Because remember, the coefficient of determination, R squared, says what percent of the response variable is directly attributed to the explanatory variable. So let's look at this problem. Let's stop the car. I want to know, how is the braking distance of a car related to the tread that's left on the tires? So researchers collected data on braking distance measured in car lengths for a car making a panic stop in standing water, along with tread depths of tires measured in 1/32 of an inch. Here's the linear regression output for 3 different models with residual plots for each model. This first model is based just on the original data. So we did tread depths, we did straight up tread depths and stopping distance on car lengths. And then model 2 and model 3, we're going to have to find out what transformation was involved for that data. So if I want to know, so here's model 1. They gave us our residual plot and they gave us the summary data right here. We have our constants, we have our slope. We have an R squared of 0.822 and all that good stuff. And if you want to find R, just take the square root. Model 2 involves taking the natural log of both sides. We're taking the log of both sides. Here is my residual. Here's the R squared. That's what we're going to be looking at. Oh, that's a nice big R squared, and I don't see much of a pattern. And so this is my exponential model because I'm just taking the log of the braking distance. That's my Y. Taking the log of Y, that's the same as X being raised to a power. Or x being the power, I'm sorry. But we notice clearly there's a pattern right there in my stopping distance. So let's figure out which of those did the best job of summarizing the relationship between tread depth and braking distance. And then let's predict how long it's going to take my car to stop. Let's interpret the residual for the trial. All right, so what I did, go back, look at your residual plots. Which residual plots has the most random of patterns? And the one that had the most random patterns is the one where we took the natural log of both sides. You can also do log. It doesn't matter which one you use, just do the same on both sides. So because the model that uses x equals the natural log of thread depth and y is the natural log of braking distance produced the most randomly scattered residual plot with no leftover curve pattern, it is the most appropriate model to use. Also, its R squared was closest to 1. So this is the most, use the words they use. I'm going to say it did the best job summarizing. So it is the one that is the most appropriate model to use. Now they want us to calculate and interpret the residual for a trial when I know the thread depth and I know the stopping distance. So I'm going to take the equation that we came up with, our model, and we're going to take the natural log of braking distance, and we're going to figure out how many car lengths it takes us to stop. So because I'm taking the natural log of the braking distance, we're going to do natural log as base E. So I'm going to do E raised to this power equals the braking distance. Remember, base raised to the power equals my Y. So I predict it should take 13.57 car lengths for these cars to stop. Well, we were told it actually took them 13.6 car lengths to stop. So to find our residual is y minus y hat. I'm sorry. y hat minus y. So we got 0.03, which means it actually took us 0.03 car lengths longer to stop than we thought. So when the thread depth of the car was 3.32 inches, the car traveled 0.03 car lengths further than the distance predicted by the model. That's what my residual means. Now you're gonna here's some instructions on how, if I give you a list of data, here is your list on how, your instructions on how to put that into your calculator. So make sure that you can do that. If you've got questions, ask me on Wednesday. And here's a thing for you to practice. Compare it to your actual fish results from other videos. Make sure you're doing it correctly. All right, let's do one more together. So one sad fact about life is that we're all going to die someday. So many adults plan ahead for their eventual passing by purchasing life insurance. Many types of life insurance policies are available. Some provide coverage throughout an individual's life, which is called whole life insurance, while others last only for a specified number of years, which is called term life. The policyholder makes regular payments. Those payments are called premiums to the insurance company in return for the coverage. When the insured person dies, a payment is made to designated family members or other beneficiaries. So basically what you're saying, if you don't know how life insurance works, is that every month you pay somebody with the anticipation that if you pass, your family will get some money so that they can take care of bills because you're no longer there to help them financially. So very, very selfless thing to do. You should totally look into it. So how do insurance companies decide how much to charge for life insurance? They're not doing this for free. They need to make money. So their goal is that you will pay money and not die. That's their goal. And then you have to get a new insurance policy later. So they rely on staff of highly trained actuaries, people who with expertise in probability, statistics, and advanced mathematics to establish the premiums. For an individual who wants to buy life insurance, the premium will depend on the type and amount of the policy as well as the personal characteristics, age, sex, and health. The table shows monthly premiums for a 10-year term life insurance policy worth $1 million. What this means is every month for 10 years, you are going to pay in a certain amount of money, and if you pass within that time frame, your loved ones will be given a check for $1 million. That way, on hopefully what will be a very sad day for them, they can still pay the bills. So they created a table. A 40-year-old is going to have a monthly premium of $29. A 45-year-old pays $46 every month, and so forth and so on up until 65. Notice the premium increases because the older you get, the chances are you're not going to make it through the 10 years. Because once you lock in this price, you pay it for the entire term. So that's what they're saying. This guy living to 65 is much less likely to happen than this guy making it to 50. So that's why the premiums go up. So then we generated some outputs. So the outputs, the three possible models for predicting monthly premium from age. Option 1 is the original data. This option right here, based on the original data. Options 2 and 3 transform the original data. Each set of outputs includes a scatter plot with a least square regression line added and a residual plot. So notice my original data. So when I'm looking at this, I'm like, all right, that's not bad. The data is fairly close to the line. But then when we look at the residual plot, you can definitely see a pattern right here. And that's my original data, just the premium and age. When we transform the data, I take the log of both sides. I'm taking the natural log of y. I'm taking the natural log of x. Notice when we do this, the points all get closer to my regression line, my least squares regression line. But r squared, the residual plot right here, still has a pattern. However, r squared is 0.99, and darn, that is very close to 1. Then on the third option, where what we did is this is an exponential model because we just took the log of y, which would be the same as having x as my exponent. Man, notice that we even got closer to the line than we were. There doesn't appear to be any distinct pattern with my residual plot, and r squared is actually 1. It actually got a little better than that 0.99. So they want us to use each model to predict how much a 58-year-old would pay for such a policy. And then which model does the best, because 58 wasn't on the list. We counted by 5 years, so that 58 would be a gap. He would have a different premium than the other ones. So, and then which model does the best job summarizing the relationship between age and monthly premium? And then explain that answer. Alrighty, So let's go ahead, and I want to know what happens if I use each model to predict the premium. So if I use the first model, the left graph, option number 1, this is option number 1, where it's just the straight up least squares line from my original data. I'm going to take 58 and I'm going to plug it in for age. So I predict that I am going to pay a monthly premium of $157.54. My next question is going to ask, should I use that? Should I use 157 as the actual model? Now for this option number 2, the center graph. Option number 2, which they said my equation was the natural log of the premium equals, well, you can read it, and take a natural log of the age. If you remember, I said the residual plot didn't make me very happy on this one. So I'm going to plug it in. So I'm going to take the natural log of the premium. Notice I said predicted premium because that's what I'm actually predicting it. Plug in the age of 58. I'm just going to plug all of this into the calculator just like this. And you'll see natural ln is a key on that calculator. So I work it out. And so I'm going to get natural log of the predicted premium is 4.9509. The more decimals I use, the more accurate my answer will be. Remember, this is base E. So I'm going to do E to this power is going to be my premium. So if you do shift ln, it'll bring up E on your calculator. And I bang it in and I get 141.30. And it went on, but since we're talking money, I only did 2 decimal places. This model predicts that a 58-year-old will pay monthly premiums of $141.30 for $1 million life insurance policy. And then my last one, graph 3, or the right graph, I just took the natural log of Y, the premium. So when I plug it in, notice this natural log of 4.9192 is just a little different. This is 9509, 9192. They're a little different. The model's a little different. So I take E raised to this power, and that's going to give me my premium. So this gives me a predicted premium of $136.89. So this model predicts a 58-year-old will pay monthly premiums of $136.89 for $1 million of life insurance. That's term life insurance. At the end of 10 years, it would expire, and I'd have to do it all again. Now, the next question says, which of those does the best job of summarizing it? So this is where we look at our residual plots. Which residual plot was the most random? And if you remember, we already talked about this. Option 3 is the most random residual plot. Look how random that is. Also, the coefficient of determination is very close to 1. So the exponential model, the right model, option 3, it's exponential because I'm only taking the log of Y. This does the best job of summarizing the relationship between age and monthly premium. Notice I am hitting up all my points. I am putting everything into context. And I'm using the words they used. They used best job. I use the words best job. This model best predicts the amount of monthly premium from age because the residual plot is the most random. I am telling how I knew it. You have to tell how you knew it. Because the residual plot is the most random plot of all the options. And option 3 also has the greatest R-squared value. So don't be stingy with your words. Write down what you need to say. Say everything and then go from there. All right, if you've got any questions, Patriots, make sure you jot them down. And you'll notice your summary is next. Go ahead and review it. It talks about what makes a power model, taking the logarithm of both sides, our exponential models. And then we're going to go ahead and we are going to finish up assignment 3.3. So I have assignment finished for 3.3. Be ready with your questions on Wednesday because that's what I am dedicating Wednesday to. Have a great one, Patriots, if you choose to. And I'll see you when I see you.